Just getting the stream set up, ready to go. Okay. Hey there, Viempol. I'm just getting things set up real quick and then we'll get started. Okay. Audio sounding good? Here. Oh, good. Okay. Oh, nice. Just got off work. That's good. I mean, I'm assuming it's good. Okay. And let's get this all set up. Perfect. Font size too small, too big. I know that the docs is going to be, the PDF's probably too small. But that might just be what it is. Why is that not working? There we go. Okay. All right. Today, we're going to continue working on the. Okay, perfect. We're going to continue working on the line number program stuff. So where we left off last time was right before I ended. I just finished up reading in the. This isn't the right spot. We'll mark this to come back to, but I think it was here. Yes. Where we left off last time was actually reading in the line number header. Made some changes, like default is statement. I had it as a U8, but that clearly is it's a Boolean value, so made some fixes there. And then added in all this code here to read in the actual header of a line number program so that we can then start working on building out the matrix as described last time. So that's the goal today, is to start working on the line number program kind of interpreter, which should be fun. So let's make sure I've got everything I need. I think the only other one I want to have open is the debug info. Okay. I'm going to build it real quick just to see. I think I left it in a failing state. Yes. So we need to fix this. This should be debug info, or no, dwarf dot. Version 5. Okay. And then I need to actually import dwarf, const dwarf equals at import // dwarf .zig. There we go. And that, yeah, okay, everything is compiling again, which is good. So, got that. Let us fix that. I think that's, yeah. Fix, move, what's it called? Version constants to dwarf module, or to dwarf.zig. There we go. And that is done. Okay. So let's go back to line number program. So what I've got here is a line matrix. And right now it's not doing anything. It's just getting an empty or multi-array list of the state. And then it's initializing that state as described in the documentation. So in the documentation, these are the initials. This is the initial state of a line number program. And so I just wrote a little function here that we can call that will use that. Or use that to create initial state object for us. And the only thing that actually is variable with initial state is that default is statement value, which comes from the header. So now that we have that, we can set these things. And I've actually used a pack struct here because in the state, there's a whole bunch of values and there's a whole bunch of 1, 2, 3, 4, 5. Yeah, 5 Boolean values. And rather than wasting all those bytes, I don't know, since we're doing multi-array list and trying to pack it, and there's gonna be a lot of these, I thought, why not try to pack these in so that we only have to use 1 byte for all these Booleans. We'll see if it works out well or not. Okay, so I think the first step is, now that we have those, is to kind of read through this. In the there's going to be 3 kinds of opcodes. There's special opcodes. They have no field and operand. They are special, and then, oh gosh, go back to where we were. There we go. Sorry, there we are. Okay, they're special in that each line number header can define the range of these opcodes, and I'll show you later in the docs what it means. It's kind of interesting, kind of confusing. Then there's the standard opcodes. Those are fixed, and they have a fixed set of operands, which I think is interesting here. It says these have a U-byte opcode field, which may be followed by 0 or more LEB128 operands, except for dwarf LNS fixed advanced program counter. See section 6.2.5.2. The opcode implies the number of operands and their meanings, but the line number program header also specifies the number of operands for each standard opcode. That to me is crazy. It means that we probably don't need this. Like, we don't need the standard opcode lengths, which means we don't need to allocate this and do this mem copy. We can just skip it. So that's what we're going to do for now. I'm going to leave it uncommented, or just commented, and say note. According to the standard, the opcode, standard opcodes have a specific have an implied number of operands each. So we don't need this information here. So what's crazy to me is why they encode it that way. It seems like a waste to me. But I'm sure that we'll come around and figure out why we need it. So that's why I'm only commenting it out right now. I'm going to put that up here as well. Anyway, so now instead of const, what we need to do is r dot toss. Basically, we need to toss the opcode base minus 1. Opcode base minus 1. And yes. This Jeep, yep, this is unused, so we don't need that anymore. We don't need this anymore. And yep, we don't need even a deinit anymore. And this function, we defer here. We don't need that. Which means we probably don't need it up here as well. Must have already gotten rid of it. Oh, no, there it is. Okay, everything is back to compiling. Let's just make sure it all works. Everything works as it did before, which is good. So that was a good little change there. Okay. Back to the documentation. We also have extended byte opcodes. These have multiple byte format. The first byte is 0. The next bytes are unsigned ulib 128 integer, giving the number of bytes in the instruction itself. Does not include the first 0 byte or the size. The remaining bytes are the instruction itself, which begins with the ubyte extended opcode. Okay, and I think those are elsewhere, so we can look at that. And line number header, which we've already parsed, so we're going to skip all that for now. Those will come in specifically in more, but okay, standard content descriptions, we already did that. Vendor defined. Okay, the line number program. All right, so as stated before, the goal of the line number program is to build a matrix representing one compilation unit, which may have produced multiple sequences of target machine instructions. Within a sequence, addresses and operation pointers may only increase. Line numbers may decrease in cases of pipeline scheduling or other optimization. Special opcodes. Each ubyte special opcode has the following effect on the state machine. Add assigned integer to the line register. Modify the operation pointer by incrementing the address and op index registers as described below. Append a row to the matrix using the current values of the state machine. Set the basic block register to false. Set the prolog end register to false. Set the epilogue begin register to false. Set the discriminator register to 0. All of the special opcodes do the same 7 things. They differ from one another only in what values they add to the line, address, and op index registers. Instead of assigning a fixed meeting to spit, there's a whole reason for this. So a special opcode value is chosen based on the amount that needs to be added to the line, address, and op index registers. The maximum line increment for a special opcode is the value of the line base field in the header, plus the value of the line range field minus 1. Line base plus line range minus 1. If the desired line increment is greater than the maximum line increment, a standard opcode must be used instead of a special opcode. So they're special because it allows it to be much more compact. That's my understanding. The operation advance represents the number of operations to skip when advancing the operation pointer. The special opcode is then calculated using the following formula. Opcode equals desired line increment minus line base plus line range times operation advance plus opcode base. Yeah, the all these, it's I'm not quite gathering it either, but I think, yeah, Appendix D's got an example. So we're gonna look at Appendix D here in a second. Let's just go do that right now, because I believe what we'll need to do is calculate. I've done this before, and then I deleted all that code. So I believe we need to calculate these opcodes so we can figure out what the range. Yeah, let's take a look at Appendix D. It'll make sense. Examples, line number example. So here's the header, special opcode. Suppose that a line number header included the following header fields not needed are not shown. Okay, so you had an opcode base of 13, a line base of -3, a line base can be signed. I do not account for that. I thought that was an unsigned number. We will need to fix that. I think that's a bit cast. Expected one argument found there. Okay. Yeah. Maybe if I paid more attention, I would have known that the line base was negative, but there you go. So line base is -3, a line range is 12, minimum instruction length is 1, maximum operations per instruction is 1. Okay, this means that you can use special opcodes whenever two successive rows in the matrix, so you have one row and then another row in the matrix have source line numbers differing by any value within the range -3 and 8. So basically, if the lines are within this, you're at one line, you're allowed to go back 3 lines or forward 8 lines between each successive row in the matrix. That's like special local range that you're allowed to operate around. So that's what the special opcodes are for. Because of the limited number of opcodes available, there's only 256 opcodes roughly available. And see, so going back in the matrix, have source line numbers by any value differing within the range 3 and 8, and because the limited number of opcodes available, when the difference between addresses is within the range 0 and 20. And they'll show how they calculate this. The resulting opcode mapping is shown in figure D.34. Note that the bottom row of the figure is not all line advances are available for the maximum operation advance. So we have a lot of things going on here. Let's see, Excalidraw. Yeah. Come on, where's the hand? So we've got, just to take some notes here, we've got opcodes, we have addresses, and we have lines. Okay, so opcodes are from the line number program. Address is meaning the actual address and the actual instruction program counter address, right? Actual PC address. And then line is obviously source stuff. Okay. I am not very good at writing with that pen. Okay, so you build out this kind of table here where you have -3 through 8 by 0 through 20. And then you have basically not 256 because you have to skip the 12 standard opcodes plus any if there's any extended opcodes that are being used. And so that's where the opcode base comes from. Starting at 13, you did an outline, 13 through, so what's first 11? Is that right? Yeah, first 11 are for an operation advance of 0. And the next 11 are for an operation advance of 1. So that if the instruction goes 1, and imagining that's 1 byte. Yeah, obviously. When the difference between addresses, yeah, is that. So interesting. I'm not sure how many instructions where the operation would advance 0 bytes. I guess there's got to be some where that would happen. Why is it so complicated? I'm but a humble implementer of this. I'm sure that they have reasons, but it is difficult sometimes for me to ascertain why it's so complicated. There is no requirement that the expression 255 minus line base plus 1 be an integral multiple of line range, which we see here. 255 minus 13 plus 1 does not evenly divide these, which means that if the operation advance is, for example, 20, if you're jumping 20 bytes down into the program counter, you can only go backwards in this situation. So if you're outside of this range, then you have to use the standard opcodes. Okay, so I think what we need to do is define these, this range here. So if we go back to line number information and we just jump down here. Aha, this is where we were. Let's start doing stuff, say. Define the special opcode ranges. So let's see, line const. See, a special opcode value is chosen. A special opcode value is chosen on the amount that needs to be added. The maximum line increment for special opcode values. Maximum line increment for a special opcode is the value, the line base field in the header, plus the value of the line range field minus 1. So if we look at the header again, they're saying this, the difference between these two, this I8 and this U8, are what? Oh, that's going to cause problems. I guess it's going to be fantastic. First of all, I do want to check to make sure, sorry. Is that, did it say signed? Is what I'm curious about. Oh, it is. See, yeah, S byte. I just said byte and I move it. Okay, so it is a signed byte. Okay. All right. So we have so basically what we want to do is be able to know with the opcode, we want to say like fn calc opcode, calc special opcode. And we should take in we don't need the whole header. What we really need is line range. We need line base and opcode base. Now this is sorry. Part of what's complicated about the dwarf format is they were writing for both implementers and like both people who are like compiler authors and then people who are writing debuggers. And so when they say how you calculate this, that's actually what do I call it? Like the compiler author cares, because when he writes this, or he or she write the implementation to generate dwarf data, they need to know what opcode to choose. And so, hey, they know what desired line increment they have. They know how much the operation needs to advance. Then they calculate. It might be that they're also writing for non-humans. That's true. Definitely not for me. It takes a while to parse this sometimes. So I'm glad I'm not the only one. When the maximum operations per instruction is 1, the operation advance is simply the address increment divided by the minimum instruction length. I don't even know what that's supposed to be talking about. To decode a special opcode, this is what we want. This is what we care about. So it should be like decode special opcode. And what you need is we're just going to pass in the whole header, even though we don't need everything in the header. And that might be, we're just going to point a pointer to the header, const pointer to the header. Oh, if I knew how to write Zig, I would do this right the first time. Line header. And okay. So yeah, what we need is to decode a special opcode, subtract the opcode base from the opcode itself. So we also need the opcode, which obviously makes sense. Opcode, and that is going to be a U8. And so that's where I think it's why they use these special opcodes, is that they can, if most of the program can be expressed as special opcodes, meaning that most of the program isn't doing lots of jumps, then you can actually keep that debugging information. Each opcode in the line number, each adjustment to the line number program can be, what's the word I'm thinking of? Represented as a single byte. And so then it can help really condense it down. So their goal is around making sure that debug info isn't huge. But it does not return a void. We want to turn it as, we're going to turn a tuple, which is line, U8. Why not store offsets or something similar? I'm not sure what you mean. If you're talking in general, like why do this whole line number program thing, I agree. I think sometimes it would be nicer if it just stored. The reasoning for line number program is that the matrix itself is prohibitively too big to store. But the problem is I have to calculate it regardless. And so if it's too big to store, and I still have to calculate it. Now, I guess the idea is that I could calculate it on the fly. my hope is that I don't, that I'm able to just calculate it all at once and then have it stored, at least for the main compile unit. I don't know, we'll have to play around with that. So yeah, I think the line number program is a bit obtuse or opaque. I don't know. It's just arcane in a way. But it's what we got to do. So it says to decode a special opcode, subtract the opcode base from the opcode itself. Yeah, it is what it is. All right. Adjusted opcode. We're just going to copy this algorithm they got here. Opcode equals header opcode base. Now, maybe if someone came up with a different spec for encoding debug information for Linux files, that would be cool. But I'm not smart enough to do that. And I think it's I think it's worth implementing the system that we think is bad or wrong or complicated to understand why they made the decisions they did. So that if I did or if someone wanted to improve it, they'd at least know why the old system did it the way it was. Opcode header up. Right, the whole don't tear down fences till you know why they're put up kind of thing. And that should be good. Okay. The new address and op index values are given by. So the new address equals the current address plus minimum instruction length times. Oh, yeah. Interesting. Okay, that's for when we actually use it. So let's. I don't know if I like using a tuple here because I got to remember what the order is. Struct. I very likely they're because they're trying to be backwards compatible because when Dwarf version 1 came out, right? That was a long time ago. Oh, I mean we can look at it. Dwarf version 1 release. So if we look at Dwarf, oh, not that's Dwarf Fortress. Completely different thing. Dwarf debug format. 1992 is what I'm seeing. Revision October 6, 1992. So if you think about that, it's been around a long time. Their constraints were very different in 1990s than they are now. So the idea of the lines, that matrix, people didn't have as much memory and 64-bit systems weren't huge. And anyways, yeah. So definitely 1992, you were 9. I won't say how old I was in 1992, but I was not 9. Let's see. I lost track of what I was doing. Oh, yes, we're going to make a little struct here. See, const. We'll call this decoded special opcode. Hopefully I don't have to write that a lot or I'll want to rename it. Let me say, I'm going to do wait. Oh, okay. The mount increment the line register is the line base plus the result of those adjusted opcode modulo the line range. That is. So yeah, what I want is a line increment. What? New address and op index values are given by address plus minimum instruction length. So what we need to do is like a line increment and address delta. U8. Actually, no, minimum instruction length is a U8, I believe. Yeah, so what this really is a U16, right? Yeah. Because we're going to multiply minimum instruction length times the op index plus operation advance. Wait, oh no. Is this op index the one that we use here? Where's op index come from? Okay, I missed something when we're reading through here. All the special opcodes do those same 7 things. So these things always happen. Add assigned integer to the line register. Modify the operation pointer by incrementing the address and op index registers as, okay, described below. Append a row to the matrix using the current values of the state machine registers. And then set everything false, 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 0. Okay. Okay. So then they differ only in what the values they add at the line, address, and op index. So what we need is address and op index difference. Op index just to match, we're going to call it line delta. And U8 for now. So that's assigned integer to the line delta. Use. Pretty sure I8 is going to be perfectly fine within the range because you can't, the line range is limited by 255. So it's actually an, it is. Because you could have 0 to 255 and just say never, but that would never happen. Right? Use an I-16. For now. All the special opcodes do those same 7 things. They differ from one another only what they, add. Okay, so this is what's being added. Decoded special opcode. Okay. So then coming back down here, the new op index is equal to the old op index plus operation advance modulo. Okay, so this is the remainder. This is the, okay. Calculate operation advance. So we do need to know the current state. In which case, if we need to know the current state, then we might as well just say advance with opcode. Take the header, take the opcode, and we there's got to be a way to factor this out, right? So we don't need the current state to do all this. Right? Because looking at it, going back to where is the line number example here? These opcodes, it's a table. Like we should just be able to tabularly say 101 means the line advance is 1 and the operation advance is 7. And then take that information, and maybe that's all we need to. Maybe that's what I'm mixing up is I want, the operation advance. And I'm going to do the const line advance. And what we're going to do is take these, because then we just do the calculations. Call this decode special opcode. Line delta address operation advance. Okay. And we through 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Going back to the oh, I need to just figure out how to get the bookmarks to work again. Oh, I do remember I was just using wrong. Here we go. Let's mark this. Mark B. There you go. There you go. Okay. So line advance. The line increment equals line base. Header dot line base mod plus adjusted opcode odd line range. Okay. Return line advance operation advance. That typo is going to bug me. Operation. Okay, so we don't need to do that. What we need to do is we got this decode special opcode function now. What we can do is add a like FN advance special opcode wait header const line header and state. State, right? Point to state. State. And then void. Okay. Okay. So then we've got to do this fancy logic. What we're going to do is get deltas, decode, special opcode. Then we need to do not much. Yeah, I don't know when you left, but I figured out what I was missing, kind of what I was doing. So the documentation here is very they kind of mix together both the calculating of that, I don't know, square of the opcode range, basically the line deltas and the operation advance. That's what I wanted to calculate, but the calculations they have here in the docs kind of do that all in one, and that was confusing to me. But now I figured out. So we have this decoding. We decode the special opcode, and then we use those line advances to increment the state. So we got two functions: decode special opcode and advance special opcode. And so then we take the state dot things like, where did it go? Oh, there we go. Okay. Let's see, we need to take like state dot opcode op index, which is, oh yeah, right here. We want to calculate the new op index, which takes the old op index plus the operation advance and calculates the maximum operations per. So actually what we need to do is new op index equals, because we don't want to replace that one until we've calculated both the new address and the new Actually, I guess if we just calculate the new address first, that would work, right? State.address equals state.address plus state, I think header dot minimum instruction length times, this is going to get really complicated fast, op index state.op index plus deltas dot operation advance div maxus header dot maximum. That's that. Do a lot of calculation there. So what does it not like? Oh, there we go. Now we can calculate the new op index. State.op index equals, and it's basically the exact same thing as this. Except for instead of div, we mod. There. So we get the remainder there. Expected, I've got that there. Where is it not liking? I'll tell you what I'm not liking is the line bleeding over like that. Gotta have a missing parenthesis somewhere. Oh, I have an extra parenthesis. There we go. Okay. What is it not like here? Oh, undeclared line range. There we go. Okay. So now what we can do is this. We're at the reader and we need to start reading bytes, I'm pretty sure. All the standard opcodes, let's go back into the lines. Okay, just a second. So now what we need to do is, this is I think we need to just start going through the state machine, and special opcode value is chosen based on the amount that needs to be added to the line address and op index registers. The maximum line increment for a special opcode is the value of the line base field in the header plus the value of the line range field -1. Standard line increment is greater than. think what we need to do is something like this. We'll do a labeled switch and say, reader, call it reader. I don't like that. Let's call it loop switch. On r dot c r dot take see byte equals, and let's do this r dot take 1, and we're just try this. Means this can return an error, and we're gonna just say it returns a reader error. IO CR, no R. I got that all backwards. IO.reader.error. Okay. We're going to capture that value, right? No. Yes. You might need to, but what we're going to do is, if it is from, oh, we can't do that. Because the switch prongs have to be comp time known. That's the problem with switch prongs here, is that I don't know compile time because the opcode base can change. If you look up here, opcode base, the number assigned to the first special opcode. Opcode base is typically one greater than the highest numbered standard opcode defined in the specified version of the line number information. 12 in dwarf versions 3, 4, 5, and 9 in version 2. If opcode base is less than the typical value, then standard opcode number then standard opcode numbers greater than or equal to the opcode base are not used in that line table. The codes are treated as special opcodes. If opcode base is greater than the typical value, the numbers between that and the highest standard opcode and the first special opcode are used for vendor-specific extensions. Which means that you could probably still switch, but I need to, yeah. I'll need to actually parse out whether there's this is a vendor specific, what the say header dot line base, no, not line base, opcode base. Basically, we got a while r dot, I'll try r dot take 1. Basically, while we can read, we want to capture that value as a byte. And actually we'll capture it as opcode. Right? Maybe capture it as opcode. And what we need to do is interpret that opcode. Is it a standard opcode, a special opcode, or a extended opcode? Hmm. Trying to think what's logically the best way to go. Because like to determine so let's see. If this is so if opcode is less than opcode base, then it is either a standard opcode or an extended opcode or some vendor extension, right? So then let's just say if opcode is greater than or equal to opcode base, then it's a special opcode. Um, you do advance special opcode. Opcode header and state. Okay. And then we also need to then take the state dot what does it say the special opcodes do? Oh, I actually had that. There we go. Well, that's not right. Yeah, here it is. So the special opcodes. We've already got 1, 2 done. So then we need to append this state to the matrix. So what we need to do is data dot append state. That takes the GPA there. Catch and then we need to set everything back to, so then state dot basic block equals false. 1, 2, 3. Yep. We need to set the prolog o state dot is log end false. State dot is epilogue in begin false, and state dot discriminator equals 0. And is not here, so we gotta import it. C const equals at import main zig dot and then all these use now. That's used and that's used. So there we go. Is there like a read byte? Just like I want to read 1 byte. That'd be a better way than that. Expected an optional type. Okay, this is where I need to learn more of the iter. That's not going to help. Iterate bytes. Take byte. Okay. That is a method. Take byte catch null. Okay. Now it's complaining about things here because I'm actually using it. Up index. Aha. Okay. Incompatible types I8 and U8. Adjusted opcode is a U8. Line range is a U8, but then line base is a I8. So to add them together, how's that not right? Oh. I think line delta is better than line advance because you're not always advancing. Sometimes you're going backwards. So that is a better name than what they have in the docs there. Okay, what is messing up here? Expected dwarf line number found error. Yes. Oh no, not try. You're gonna fail. Catch. Error. We're gonna just fatal this one. Message. Invalid line. Everything's working again. So then we've got this special case if it's an opcode. So now we got to figure out, is this a special opcode, a standard opcode? Oh, and then we need to continue. Now, is this a special opcode? Or a standard opcode? just done special opcodes. Now let's do standard. The amount to increment, standard opcodes. If well, you know what? Actually, we don't support version 2. And that is already labeled out. So basically, we could do something like if header.line version is less than or equal to less than dwarf.version const dwarf equals at import dwarf or dwarf, then turn error dot unsupported supported dwarf version. Error too many R's in the error. Okay. Okay. I need to fix error handling at some point, but I want to get the line reading done. All right, so because of that, we can go back up to here where it talks about those line number information stuff, right? Where is it? Opcode base right here. Versions 3, 4, 5, and 12. So it's 12s and 3, 4, 5. So we know that opcode base should be 12. If it's not 12, then right, if opcode base does not equal 12, then opcode base is less than 12. We already took care of that. Opcode base is greater than 12. I don't think this matters actually. What we want to do is we still need to check if this is a standard. So if this is less than opcode base, right? Let me take the logic here. I gotta write this out. This unconditionally handles all special opcodes. Sorry, I just got a call. I need to check this. That's fine. Not important. Okay. So then it's like I want to handle all of the non-special opcodes or the standard opcodes. So let's do standard opcodes. Including opcodes that would regularly be considered, standard opcodes. Wow. There we go. Okay. So if we get to this point and it's a standard opcode, which just basically means we can switch on it and it's standard, right? So let's go to dwarf. Let's see. Const dw equals at import dot slash dw dot zig. Yeah, we have these are the standard opcodes. Line number codes. Then it is a standard opcode. So we can switch on it there. As long as it's not greater than 12. If it's greater than 12 or equal to 0, right? So then if code equals 0, this is an extended opcode. We'll handle that. Opcode is if opcode is less than or equal to, is it 12? 13, I think. No, less than or equal to 12. This is a standard opcode. Oh, wow. I like to wrap things like this in functions and add tests. Yeah, I probably should do that. Else vendor specific. Okay. Yeah. So then I think what we need to do is do advance extended opcode state header state advanced extended opcode and then something like this should be right. And then let's just do like skip vendor opcode. All right, so let's do, guess we can do advanced extended opcode first. FN advance extended opcode. Oh, actually we need the reader. That's the difference here. I actually don't think we need the header right now, but maybe we will. Actually, we probably do need the header. So the extended opcode needs the reader because it needs to read the next one to get what opcode it is. To advanced extended opcode, our header state. Yeah. So we don't need the opcode. What we need is the reader. io.reader dot just pointer to that. Header const header. And we need the state void. This actually probably will return an error. Let's just add errors down here. Error equals error set, and the error set we want invalid, invalid extended opcode, invalid line number program, unsupported version. There we go. And okay, so then we got this advanced extended opcode. We get to look at extended opcodes. The extended opcodes are as follows. In sequence, set address, set discriminator. And it says, defined file operation defined in early versions of Dwarf is deprecated in Dwarf version 5. So since we're supporting Dwarf version 4, we'll need to add that in just to support it, even though version 5 will not use it anymore. I want to just handle it. There's another place that defines special and standard opcodes right here. Extend opcodes. These have a multiple byte format. The first byte is 0. The next bytes are an unsigned integer, giving the number of bytes in the instruction itself. does not include the first 0 byte. The remaining bytes are the instruction itself, which begins with U byte encoded. U byte extended opcode. Okay. So we need to read first the length. Instruction count. Count size. Dwarf dot read U64. There we go. And this will be if we get an error catch, invalid, turn invalid, invalid extended opcode. Okay, then we got to take the first byte. So then we do const opcode equals r dot is it take byte we found, which is great. Catch, same thing. Error dot invalid extended code, and then we switch on opcode. Once again, if opcode is greater than, is there, oh man, that'd be like a max. There's got to be a max, enum max, something like that. Enum max, standard enums. Could be like a max value from the enum. That would be a very nice function to have. Opcodes. Oh yeah, see, line number extensions, LNE. And then, so this is where, okay, this is where reserved 03. I'm guessing reserved is actually what was that one they called it? A define file. Oh, I missed. Oh gosh, Dwarf 1.0 was written by the British Computer Society program. Yeah. Explains everything. That's funny. I didn't know that PLSig wrote it. I don't know who PLSig is, but a programming specialist language group, Computer Society. Yeah, that sounds right. Oh, are they really academic? Yeah, then that definitely explains everything. And here we are, 34 years later, 34 years later, working with it, which is impressive, that it's lasted and taken a hold. Sorry, if opcode is less than, is greater than. Oh, I was fixing the dwarf stuff. I was gonna name this was, define file. Define file. There we go. And I'll write like a little deprecated in version 5. Okay. Opcode is greater than that, then once again, return that error. Okay. So now we need to go and need to make sure I read this. I guess mark this. I'm gonna mark this as you. Okay. The first byte is 0. The next byte's an unsigned integer, giving the number of bytes in the instruction itself, not including the first 0 byte or the size, and then the remaining bytes are the instruction itself. So what we need is then to jump back down to the line number L and E. We're gonna mark this as B. Okay, here we are. Zoom in on that. Mark that as B. Okay. Perfect. Okay. Let's do this. Okay, oh wait, no. This, we don't need to do this at all because it can be bigger than that. Because it can have vendor, user vendor specified ones. Okay. Okay. Oh man. Okay. So let's see, what do we do with the in sequence first? Let's see, the dwarf line. We need a portable language agnostic way to describe any program structure ever compiled. You know, I've never worked with what's it called? What's Microsoft's format called? PDB, right? So I've not investigated what PDB looks like, if that's any better than the dwarf format. So I'd have to look at that. I don't know if Mac uses dwarf. Does Mac OS use dwarf? I don't know. I think Android does, obviously. But yeah, I'm not sure. Portable language agnostic way to describe program structure would be very nice. And I mean, that's what dwarf's trying to get. But the problem is that then you get features. There's features in dwarf that are there to particularly describe how certain programs are compiled that don't matter. Not like we look at inheritance and things like, then you have languages get these features and the debugger wants to be able to describe what those features do in a nice way. You kind of have to then compile that information about inheritance or this or virtual function calls and stuff like that. Whereas then if you take Zig, it doesn't have any of that stuff. It doesn't need any of that. Yeah, I'm not sure how you do it. Okay, instruction size. So the dwarf line in sequence. Okay, strips it to DSIM. Let's see, dwarf line in sequence opcode takes no operands. Okay, it sets the in sequence register to the state machine. True. Depends a row to the matrix. I'm gonna zoom out a bit on that so I can see that better. Okay, so this one is just gonna say state equals true. No, state dot is in sequence equals true. And then, oh, you know what we need? Then it resets the registers to the initial value specified above. Okay. Because then what we need to do is also have a reference to the data in this function. Just fine. Data. Data, which is a reference to, or it's a pointer to our line. Was it standard.multi array list state? And this one is going to do data.append. Oh, which means we need the GPA. Ugh. m.allocator GPA state. Okay. Which means that up here we need to add the GPA here. And I'm guaranteeing that we're going to need to do that to these as well at some point. But let's not get ahead of ourselves. Let's finish the extended opcodes. Okay, so it sets the in sequence register of the state machine to true and appends a row to the matrix using the current values of the state machine registers. Done. Then it resets the registers to the initial values. Then state equals dot init header. State dot init dot, what is it? Oh, we just do header dot default is statement. That resets it. And every line number program sequence must end with a DW line end sequence instruction, which creates a row whose address is that of the byte after the last target machine instruction of the sequence. Okay. Let's do set address. The dwarf LNE set address opcode takes a single relocatable address as an operand. Size of the operand is the size of an address on the target machine. It sets the address register to the value given by the relocatable address and sets the up index register to 0. And it doesn't store or anything. Okay, so set address opcode takes a. So I don't know why, like, okay. I'm waiting for why I needed this instructions. I guess to verify that I read it right, but I already know what the instruction size is. Address. It might be for the file thing. I don't know. Address equals r dot. Oh. What is it? Take header dot address size. And then we need to read that as an integer. So you do mem dot read int. And that read int's got to be if header dot adder size equals 8. U64 else U8 U32. Oh, is my sound drop? Or was I just not talking? Looks like, okay, let me check. Can you hear me? Can you hear me here? Let's see. Okay, can you hear me here? Is it back on? Can you guys hear this? Hmm. All right. Testing that. Is this working? Hmm. No sound. I see that you sent that no sound on the chat here. Hello? Can you hear me? Let's see this. Oh, it's YouTube. Oh, okay. Okay, sound is back. Okay. I say I missed for some reason. I might have to reconnect to Bork here because Bork isn't getting these. Bork reconnect. Quit. See Bork. Bork reconnect. Quit. Bork. Okay, sounds back. Okay, perfect. No problem. Stinking YouTube. Okay. Ooh, now I hear myself echoing. Okay. Let me turn that off and dial that down. Okay. So where were we? Oh, I was doing all this address type, address size, which means we have to do 0 dot dot adder size. Well, this isn't gonna work. Oh man, is there a way to read an arbitrary int? Let's do read int. Standard mem read int. This function cannot fail. If this is a bit hacky here. Indian. Debug info equals at import dash debug info. There we go. Okay. That just changed the address. Does not like about opcode. Use of undeclared identifier opcode. Yeah, I must have accidentally deleted it. Oh crap. Opcode equals dwarf dot read. No, dwarf dot no. R dot take byte catch turn error dot invalid. And this should be at enum from int. From int. This should be a for dw.lne. Okay. All right. Next one, define file. We need to go to a different one. So we'll take a look at define file in just a second. Let's do set discriminator, which is set discriminator operator takes a single parameter, an unsigned LEB128 integer. It's a discriminator registered to a new value. fix me. This assumes that all target machines. I don't know if this is a fix me. I don't know if I'm ever going to fix that. Are either 4 or 8 bit, 4 or 8 byte, 32 or 64 bit machines. I think that's a pretty safe assumption. For right now, I mean, I know there's machines that have smaller bit widths, but for now, let's just do that. There we go. Say dwarf line set discriminator opcode takes a single parameter unsigned this. So dw, so dwarf dot read tor equals constant discriminator equals dwarf dot read uleb 128, and we're going to read it as a u64, and actually I think u32 is what I've set it to be. So it says discriminator register to the new value. Am I missing? Oh, reader. And then catch turn error dot state dot discriminator equals D. Okay. So now let's look at how the defined file one worked. Before I do that, I need to run for a little break real quick. Bork ifk 5 minutes. Some water. All right, and I'm back. So where were we? Oh yes, we're gonna look at version 4 information. Ooh, hey. Well, that's nice. They put that. This is an appendix now. They used to just be right there. That'd been nicer. All right. Define file. The DLNE define file opcode takes 4 operands. A null terminated string containing the full or relative path name of a source file. If the entry contains a file name or relative path name, the file is located relative to either the compilation directory or one of the directories in the include directory section. An unsigned 128-bit number representing the directory index. Excuse me. An unsigned 128-bit number representing the length of bytes of the file. Okay, so this gives us directory index represents an entry in the include directory section of the line number program. The index 0 is if the file was found in the current directory of the compilation. 1 if it was found in the first directory, include directories. Yep. Primary source file is described by an entry whose path name exactly matches the given attribute name in the compilation unit and whose directory index is 0. Files are numbered starting at 1 in order. Interesting. So that was encoded in the line number information itself in the past. And when I say in the past, I mean version 4, which isn't really, I mean, most things only support version 4 right now. All right. Const mean if, yeah, define file, we're going to say if header.version equals dwarf.version 5. We definitely don't want to keep going on this. We want to just return error dot valid. Okay, so now that we know that this is valid, because we don't want to just start reading in arbitrary data just because someone coded their thing wrong. Opcode. I'm going to read, we want to get the file name. Const file name equals r.read delimiter, stream delimiter take delimiter take delimiter inclusive, the first null byte, and then if the if the entry contains a file name or relative path name, the file is located either relative to the compilation directory. Then we want to do const index, which equals dir Question is, what are we supposed to do with this information? Are we supposed to set the, I guess we set the state of the directory. Dir equals dwarf.read ulib128r. Why can't I type this? Invalid extended opcode. Here. Yank yank paste. Don't care about this one. Last mod time, which is actually probably a U64. Then number, length and bytes of the file. File size. Also don't care about here. So what we really care about is the dir and the file name. And what we have to do now is search the file names, see if that file name's been found, and it should be because we already have the headers. So what we need to do is go through and yeah, find the file and the directory. And the dir doesn't even matter. Is that not part of the state? They change the state. At the beginning of each sequence, line number or state of registers is address, up index, file, line, column. Or it may be specified by other means. Okay. So then we set the file to, this is used to set the file. This is what I'm guessing is we have to use it to set the file. Define a file. Yeah, I'm going to check to see if there's another argument here. Copy, advanced program, set file. No, so it just defines file. It's a big waste of time. We're going to do this. We're just going to do nothing. And say, this seems to be a bunch of do nothing. Just skipping the bytes for now. And we don't need this. Okay. And why is this? Okay. And it doesn't like that because we have not written the advanced standard opcode code yet. So let's do that. It's 12:20 though, and I am hungry for lunch, so I'm gonna end the stream today. But thank you for watching. I'll see you next time I can get a chance to stream. I don't know when that'll be, but hopefully soon. I'll see you.